Hello. Thought I'd start this session with Albert Einstein here, writing on the blackboard. Simple thoughts, simple solutions for complex problems. And with regard to resource efficiency, this is certainly what we need because it's very easy to make things more complex, and there's an elegance to being quite frugal in many respects, and thinking carefully about how you design a building so that it uses the least amount of resources in as simple a fashion as possible. And this is really key when you start to consider that the carbon emissions from properties. And you can see here that space heating, there in green, equates for 53% of the overall carbon emissions, which is a considerable proportion, over half. And then domestic hot water accounts for 20% of your carbon emissions, with appliances then being the next largest chunk. So we can really start to develop a simple way of prioritising how we should focus upon reducing carbon emissions. Now, of course, this isn't just about carbon emissions. It's also a case of reducing the amount of energy that we use, insofar as it helps to preserve fossil fuels, extends the life cycle of our utilisation of them, where they're necessary and where they can be used. And quite surprisingly, you might find that sometimes things like natural gas have actually got lower carbon emissions than some of the other so-called green technologies or green fuels. Biomass, for instance, has got some quite considerably high carbon emissions at the point of source where they're actually burnt. Where you're burning wood fuels or anything like that, because the carbon emissions are almost as high as that of coal. So you've got, if you're thinking about global warming, then you're thinking about some long-term effects from short-term issues, and being very careful about how you utilise fossil fuels and even renewable fuels really starts to become key. So with space heating, the thing to do is to reduce that down to as much as possible. And then the next thing would be to reduce your domestic hot water demand, with mind to electrical use, lighting and appliances. Now in the UK we've got space heating, water heating and lighting. Those are all covered by the regulations, but things like appliances aren't covered by regulations, nor is cooking. So therefore there's a bit of a gap on the map. Passive House, as a quality assurance method, actually includes the appliances and the cooking within its calculations of the primary energy demand, which is, should we say, a building physicist's view of something roughly equivalent, in a manner of speaking, to carbon emissions. I'll avoid all the complexities in the physics, but let's say there's a correlation between the two. So what we've got here is really a case of trying to think about the least cost way of reducing our carbon emissions. And on the left hand side of the graph, what you see are a load of efficiency measures, and all of these things are coming in below the line, below the zero line. Now that zero line is really important to think about, because basically what we've got is we're in this graph, which has been produced by McKinsey. It's looking at the carbon emissions over a protracted period of time until I think it's 2050. And what you see on the left, the negative numbers, are basically the cost of undertaking energy efficiency measures compared to doing nothing at all and continuing with business as usual. So, and what you're seeing is that those negative numbers are actually saying cost savings, and whereas those things above the line, which you'll see includes buildings, new buildings, all of these things are having a negative impact upon the environment. They're increasing carbon emissions, and therefore there's a cost associated with those carbon emissions, and mitigating, do what we can to mitigate those things, because a new building, even if it's more energy efficient, isn't the same as having an existing building and retrofitting it, for instance. And then if we go over further on to the right, then we've got a lot of the so-called green technologies. So nuclear, wind, we've got biomass, we've got solar PV, carbon capture, and the likes. So there's a whole series of different technologies there. Now the one thing that always strikes me is if you actually take the area of the negative, all that blue, below that 0 line, if you take the area of that sort of triangular sort of shape, and then you try to map it over the top of the more positive costs, then that's about as far as you can get for 0 costs overall. And this can start to become a way of thinking about how you can actually develop some sort of fuel policy and fuel methodology, a way of reducing carbon emissions. So what you really started to see is that from the left-hand side of the graph to the right-hand side of the graph, the life cycle costs get reduced. So you start on the left, you use all of your energy efficiency measures, that releases capital, and you're then able to invest that into the fabric of a building or other carbon emissions reduction kind of approaches. So really the first thing to do is to retrofit buildings, of course, and pay close attention to that, and playing not just for heating but for electrical energy use and the likes. But when new buildings are being constructed, they should be made as energy efficient as possible. So here we've got a graph that is showing building regulations on the left hand side, then we move over towards lower energy buildings, then we move over to passive house buildings, and then on the far right we have autonomous off-the-grid buildings. Now this graph is basically a repetition of some work that has been done by Dr. Wolfgang Feist from the Passive House Institute, but it's also been backed up with other life cycle studies that have been undertaken and presented in other academic journals. And this particular study was can be found within that overall literature review that I'm referring to. So basically what we've got here is, you can see that the blue indicates the embodied energy, and that's the amount of energy that goes into constructing the building itself. So that's the, if you're using masonry construction, that's the bricks and the blocks. It's for the floor slabs and things like that. If it's timber frame, then it's for the processing of the timber frame. These particular projects are basically they vary in different types in terms of the embodied energy, but you can broadly see that for the building regulations building, the low energy building and the passive house building, the blue remains pretty constant. It doesn't diminish. The passive house one is slightly lower, and that's because it's not as heavily reliant upon masonry construction in this particular study. Timber, if it's a timber building, then you'd expect those embodied energy levels to be lower again. But over on the right hand side you've got the autonomous off the grid building, and you can see it's got a much higher level of embodied energy, and the reason for that is because you've got all the bolt-on paraphernalia. You've got the solar thermal panels on the roof, you've got the photovoltaics, all of these kinds of technologies. If we then start to look at this kind of reddish layer, then that's the maintenance energy. So here we've got the replacement of boilers and the likes for the building regulations and the low energy buildings, and we've also got, for the passive house buildings, we've got replacement of MVHR systems, and for all of these 4 different building types you've got replacement of windows and the likes. But on the right hand side, the autonomous off the grid building, we've got the replacement rates for the photovoltaics, the solar thermal and other bolt-on technologies. So therefore the embodied energy is that much higher. So what we've got here is we've got a power station piggybacking on your home, and the amount of primary energy, the amount of energy that's used to construct a building is that much higher and over its life cycle. So really you've got to question whether that is entirely the most appropriate approach, and whether you might be thinking whether a district system, a district energy system of some sort might be more beneficial, or even something more central, of a centralised solution. And then if we start to look at the yellow, that's the energy in use. So you can see how a building regulations building has got a certain amount of energy that it uses over time, and because this is a life cycle study looking at a period of over, I think it was 80 years, and you can see how the building regulations building, the yellow bar, is multiples of the embodied energy and the maintenance energy. So really the focus there is actually saying, well, people talk in environmental terms about embodied energy of the building and the maintenance energy, but the real thing to focus on is actually the energy use. So then you start to move over to the low energy building, and you start to see that there's some improvements that have been made because of improved insulation or reduced thermal bridging or some other technical criteria. And then it's better, but it's not fantastic. So we start to look at the passive house building, and here we've made some massive reductions, around about a 90% reduction overall. So in terms of peak load here, it looks around about sort of 80% or so. But if you then look at the autonomous off the grid building, well, the amount of energy use is actually very similar. It hasn't really changed. So you've got to sort of add some more questions into this kind of process. And really what you start to land on is that your optimum is somewhere around the target of passive house. I'm not going to say it's absolutely passive house. There are always discussions about where where this little miracle line is, but if you buy into passive house, and I agree with a lot of the principles about passive house in terms of the quality assurance standards that underpin it, then then you're really digging down to this sort of territory. But ACB Silver can also be something that's complementary to that. It's more of a low energy solution than a passive house, but it uses the same quality assurance methods, and you actually find that the amount of energy use will be significantly lower than the low energy building here in this particular example. So here we've got a range of different building types, and we've got the UK dwelling stock on the left hand side, and then we start to move through UK building regulations of 2002. We've got an energy survey from 2004, Swedish building codes from 1980, and you can see it's gradually diminishing over time. German building regulations from 1995, and then we go over to the ultra low energy homes survey that was done by Energy Advisory Associates. This was, I think it was in 1996, so this is the UK's kind of best stuff from 1996. Then we've got the Canadian R2000 standard, which was developed in 1984, and it's still one of the world's leading energy performance standards. We've got ACB Silver on the right hand side, followed by, or ahead of that I should say, really is the passive house. So really this shows how much less energy the passive house uses compared to the rest. So once again we've got taking on board the lessons that we learned from that McKinsey study. What we find is that we're not only reducing our energy use by 80% compared to 2002 building regs, and actually more or less, strangely enough, still compared to current day building regulations as well. And then what you're getting is least cost life cycles tracking from the left hand side towards the right hand side. When we start to look at renewable technologies, if you believe in what I feel is a mythical kind of zero carbon status, because basically it's an accountancy game, it's not reality. Until the national grid is completely zero carbon, then you'll never get a zero carbon building. If it's an off the grid building, then we've already looked at that. So what you're seeing here is we're along this baseline is mapping the reduction in the amount of renewables that are required to basically balance off the energy that's used above the line to heat the building, provide cooking, etc, etc, etc. And you can see that the least amount of bolt-on technologies are required with the passive house building right over there on the right hand side. So if you are an aficionado of zero carbon and that kind of thing, then certainly getting the fabric right first starts to make the most sense in terms of getting the overall energy balance of a building right. Okay, so where do we go? Well, the more energy that you use, the more renewable technologies that you need to offset your carbon emissions, and that costs money. PV and the likes costs an awful lot of money, and you may be able to tap into various different subsidies and the likes that are around, but at that truer level, you're having a subsidy from somebody else to achieve something, and it's questionable in terms of that overall macroeconomic scale. And the other thing to think about is the maintenance issues associated with the bolt-on technologies. and other renewable technologies. I would tend to argue that we should be sticking to something that's a little bit more simple and easy to maintain, because we've all got busy lives and the last thing we want to be doing is fiddling with other engineering bits of kit, unless of course you're an engineer, in which case you might enjoy that kind of thing. So here we've got, once again, life cycles tracking from left hand side towards the right hand side, but I'm questioning to some extent whether this zero carbon approach is what we really want to do. But I'll work with you on a project if that floats your boat. But we'll make sure that we get the fabric right in the first place, so that you're not spending your money in the wrong places. Okay, so low energy. Low energy equals low carbon. So therefore you can have a low energy building, and by right that will have mitigated or minimised the amount of carbon emissions that it's actually making. Whereas a low carbon building doesn't necessarily mean a low energy building, because you've got biomass. You could have a very inefficient castle that's uninsulated, and you might be able to say it's zero carbon because you're burning some biomass, some wood, to compensate for those so-called carbon emissions. And it might be low carbon, but it's certainly not low energy. You're using an awful lot of energy to get there. So therefore you've really got to question what's going on, and biomass prices are around about 30% higher than that of natural gas, so it's quite questionable as to whether you really want to go down that kind of an approach. And there are even instances of residential scenarios and for school and things like schools where people have put in the biomass, and then the engineers have said, can we put some gas in as well? And therefore you're now paying for 2 lots of heating equipment, which may then not be maintained appropriately. So you've got to question whether that's the best approach. Perhaps you're better putting that money into achieving a lower energy solution. So what we've got here is low carbon doesn't necessarily equal a low life cycle cost, because if the cost of the biomass is that much more, then you've got to question whether that's an appropriate approach. And if you're concerned about your fuel bills and the likes, then it's certainly something to think about. So, as I've just mentioned, there's often this requirement where you've got biomass to have a backup boiler, and that's not always the most sensible thing to do, especially when somebody decides that it's easier to switch over onto gas from day one because it's easy to maintain, and then you've gone and wasted all of that money on your biomass. Okay, so that's a little bit of a background, a bit of a context, shall we say, for resource efficiency and actually thinking about how you utilise your building in some form, and the ways that you might think about designing the fabric first so that it minimises the amount of energy you uses before you start to think about other paraphernalia that you might bolt onto the roof, or actually reducing the embodied energy. There are some very strong kind of arguments, you say, in terms of resource efficiency, to actually also think about the nature of the materials that are getting used, and thinking about it also from the perspective of health and well-being, because you might be able to find something that is particularly resource efficient, that also has a negative impact upon indoor air quality. And strangely enough, this kind of thing can happen with buildings that use a very large proportion of timber as their finishes. That's probably going to get a bit technical, so I'm going to leave that one alone. Okay, so anyway, I hope that you've found this short training video useful, and if you would like to hear more about this kind of thing, then please insert your details below, and I will get you on the newsletter list, and you will be able to get some updates from me about this kind of thing and other design related issues that could influence the design of your home or the building that you're looking to have developed. Okay, alright, well, thank you very much, and I'll speak to you again soon. Cheers.